our last discussion, we started talking about the evidence for evolution, and we said that this essentially boils down to three different kinds of questions. The first question is, do species really change? And we saw with multiple examples that the answer is yes. Then the question was that do species or can species arise from existing species, and the answer was again yes. And then the third question was that given all this, can we really say that all the biodiversity around us has actually arisen due to descent with modification, and that is what we are going to now consider. Now, before we get to this, the major question that we need to ask is, what exactly do we mean by the term descent with modification? So, descent with modification refers to the notion that species change over time, which finally leads to the formation of new species. And what exactly are its implications? This is what we have, in order to understand its importance, that is what we are going to look at. So, let us assume that in whatever we are going to discuss, time flows from top to bottom, and let us say we are starting with an ancestral group which say has faces. So, at some point due to descent with modification, this divides into two groups. One of them basically retains the ancestral properties and just continues to have faces right till the modern times. The other one, while formation, it somehow acquires a mutation or a bunch of mutations, due to which let us say it starts now having eyes. Now, this species, this group at some point again splits into two. One group has, let us say, ears on top of the eyes, and then that group does not change any further, and it essentially comes down to modern times with ears and eyes. The other group, let us say it acquires another mutation or another set of mutations, by which it now also acquires a mouth. And let us say the process continues, and at some point this one which has mouth, it splits into two. One of them essentially just continues the ancestral state of having a mouth, whereas the other one now let us say adds a tongue to this. And let us assume, just for the sake of discussion, that this group now stays as it is. So, that finally, if you look at the present times, you have 4 species which look somewhat like this. Now, remember, this information I do not have, okay, whereas this information I have, these 4 kinds of species. Now, if I look at these 4 species, this automatically leads to what is known as a nested hierarchical organization. What do I mean by that? So, if you look at it, you have, let us say, this species right at the on the right hand side, which has a face, has an eye, a mouth, tongue. All organisms have this, therefore, we can recognize it as a species. Now, you have another nearby species, let us say, which has everything else, but does not really have the tongue. So, now you can take this species and this species and you can group them together, because both of them have the common properties of the face, the eye and the mouth, right. So, if you call this innermost group as the species, you can probably now call this group and this group together as a larger group, say something like the genus, right. Now, you can extend the process further, and you can compare these two and then also include this one, which is different from these two in not having a mouth, but you can take all these 3 as some group of organisms which only have face and eye common, and you can call this a higher order. Let us say you call this whatever you call this, let us say a family, right. And similarly, now you can take all 4 of them together and make them some hierarchical group of organization which only has face as the common property across all 4 of them, and let us say you call these things as whatever class, let us say, right. So, you can see where this is leading to. This is exactly what Carolus Linnaeus was trying to do when he was coming up with his scheme of classification. And please appreciate, Carolus Linnaeus was not the first person to do this kind of nested hierarchical classification of living organisms. His was of course the most well known, the most thorough and comprehensive, but this kind of nested classification is much older. I mean, even Aristotle is known to have done some kind of classification like this. So, descent with modification explains very nicely why this kind of a taxonomic classification is possible to begin with, and also appreciate that this kind of classification can be done for multiple groups. I mean, you can do it for animals, you can do it for plants, you can do it for fungi, etc., etc. So, descent with modification trivially explains why is it that one sees the ability to do such a thing. However, here we are going to have a problem. Remember, we are trying to see if there is evidence for descent with modification. So, the fact that this kind of a nested hierarchical classification is possible, does that necessarily imply that therefore, all these organisms are evolutionarily related to each other? So, this is like that logical fallacy that we were talking about, affirming the consequent. Okay. If A will lead to B, B has happened, does that mean that A has caused it? So, just to put it formally, just because one can produce a scheme to arrange things, that does not guarantee that the things that have been arranged have some kind of a relationship with each other in terms of how they were produced. So, just to give you an example, suppose you go to a library and you see that the books are very nicely arranged. Typically in any library, the books are arranged by topics, right. So, you have, let us say, all the science book on one side, all the social science books on another side, all the literature books on another side. In the science sections, you find, let us say, the life science books arranged together, the physical science books clubbed together, the chemical science books clubbed together. Then within the biological sciences, you have, let us say, whatever, biochemistry books together, evolution books together, ecology books together, and so on and so forth. Now, this is exactly the kind of nested hierarchical scheme that we are talking about in the context of Linnaeus and taxonomy. But in the context of the books, just because you have this kind of nested hierarchical classification does not really tell you that one book arose from the other book, right. In fact, you know that they did not arise that way. Most of the books actually arose independent of each other, correct. Therefore, the fact that such classification schemes are possible by itself does not guarantee that descent with modification has happened. So, how will you solve this problem? What happens if we take the same objects, but we try to classify them using some other properties? So, remember, when we were classifying those emojis, we classified them based on the presence of let us say, ears and eyes and so on and so forth. Can you do it using something else? Okay. So, if the organisms that you are classifying, if they have not arisen through descent with modification, then you do not really expect that using different schemes of classification will lead to similar results. On the other hand, if they have indeed arisen through DWM, if they are related to each other, then we expect the results to at least be roughly similar. Okay. So, just to again go back to our library analogy, suppose instead of organizing the books by, let us say, subject, let us say now you organize them alphabetically by, say, the author's name. Okay. So, all the books which start with whose author's name start with A, they are grouped together, all the books whose author's name start with B are grouped together, and so on and so forth. Whatever arrangement you now get, do you really expect that to be the same as the arrangement that you get when you arrange them by subject? Obviously not, right. That is because, as we pointed out, the books are actually not related to each other. They were not, one book did not give rise to another book. However, in our context, if we end up, instead of using morphological features, if we end up using some other information to do these evolutionary relationships, to figure out how they are related to each other, or even taxonomically how they relate to each other, then what is going to be the result? But before we ask that question, we have to ask what other information can we use? and this is where enters molecular taxonomy. So, if you remember, when we were dealing with the history of the subject, we said that as soon as people figured out how to sequence proteins and how to sequence genes, one of the first things that they did was they ended up trying to sequence proteins and genes from other species and then trying to figure out what are the relationships between those organisms based on those sequences, right. And just to cut a long story short, turns out that there is a very good degree of overlap between the results of traditional and molecular classification schemes, particularly at higher taxonomy levels. So, at the level of the class, the order and the family, the relationship that you get based on morphological versus molecular methods, they are very close to each other. The evolutionary trees look very close to each other. The lower you go, in the sense at the level of genus and the species and so on and so forth, that is where you end up classifying one species from one genus to another genus and so on and so forth. Now, if you think about it, this is not very unexpected. Why? Because the number of morphological traits that are available for you to do the classification is actually much less compared to the amount of molecular information that is available to do the things, okay, in order to figure out those relationships. Therefore, the degree of certainty and the degree of resolution that you will have from any molecular scheme is far greater than the degree of resolution that you are going to have from a morphological scheme. Hence, a better way of comparison is actually to compare trees that have been made based on one molecule, one kind of molecule, with let us say another kind of molecule. So, let us say protein A, compare it with protein B, or gene A, compare it with gene B. And again, just to give you the spoiler straight away, even when you do it this way, turns out that the relationships, also technically known as phylogenetic trees, that you construct using multiple genes or multiple proteins, more often than not actually lead to extremely similar results. However, before I give you examples of that and show you what I mean by very similar, what degree of very similarity, I first need to take a quick digression, and we need to discuss what exactly is a phylogenetic tree. I am sure you have heard of this term now and then, and how can one construct it using particularly molecular sequence data. Okay. It is not obvious how one can do it. So, just to ask what exactly is a phylogenetic tree. A phylogenetic tree is a graphical representation of the evolutionary relationships between biological entities, and when I say entities, you can make it in terms of relationships between species or relationships between proteins or relationship between genes, whatever. Okay. So, to give you an example, let us say we look at humans and we look at the two close relatives, chimpanzees and bonobos, and we ask the question that what exactly is the way in which these species are related to each other. So, this is the form that the relationship takes. In a moment we will discuss how we get to this kind of a form, but for a moment let us assume that this is the nature of the relationship. So, what I want to show you is how exactly does one reach here. So, in these kind of diagrams, time runs from one end to the other. It can be from top to bottom, bottom to top, right to left, whatever, but it will always be shown in which direction it is running. So, for example, in this particular case, time is running from bottom to top, right. So, on one side, on whatever is the present side of time, you are going to have the three existing groups, which in this case are humans, chimpanzees and bonobos, H, C and B, right. Now, these are the existing species, and therefore, these three have not yet led to something else, which is why they only have their ancestors being connected to them, but they do not have anything else to which they are connecting, which basically means that these are at the terminal ends of the tree, and that is why these are known as the terminal nodes, right. Now, if what I am showing you over here is what is the ancestor from which these two guys, the chimpanzees and the bonobos, have arisen. So, if you look at it, this is the one which is marked with a D. So, this graph is showing that this D is the common ancestor for both chimpanzees and bonobos, and this line which is connecting this common ancestor to the existing species, this line is what is known as the lineage or branch in relationship with a tree. Now, this relationship is also showing that this common ancestor of chimpanzees and bonobos, this itself arises from another ancestor known as G, and this G is the what is known as the most recent common ancestor for this particular group. So, for all the three species that I have, this G is the most recent common ancestor, and this green thing over here, this is what is known as the root. This is basically depicting the point that a bunch of species have, a bunch of ancestral lineages, they have come and they have led to the arising of this G. Okay. So, we are not interested in what has happened prior to G, but we are interested in G because this is the most recent common ancestor for all the three species that we are interested in. So, this is showing, this tree is showing that from G arose two different species, two different lineages, one is called E, the other is called D. From E arose two groups, one was called F, but F went extinct in this particular case, and the other group is what finally led to humans. On the other hand, as I said, from G arose D, and then D led to C and B, chimpanzees and bonobos. So, the crucial information that you get out of this kind of a tree is what is the amount of relatedness between the various species. And the simple way to think about it is that two species are more related if they have a more recent common ancestor. So, if you look at it, remember we have time on this axis, time on the y axis. So, chimpanzees and bonobos have a common ancestor in the form of D, which is roughly at this point, whereas humans and chimpanzees, their common ancestor is this G, most recent common ancestor, which is at a much earlier in time. Therefore, what we will say is that chimpanzees and bonobos, they are more closely related to each other compared to humans and chimpanzees or humans and bonobos, right. And you can see that is happening because this common ancestor for chimpanzees and bonobos is later in time compared to this one. Now, this is a very simple way of thinking about a tree. In this particular case, we are just saying time, but we are not really calibrating the time. We are not saying how much time has elapsed between this and this. There are certain kinds of trees where the length of the branch is calibrated to the amount of time that has passed. In other words, the longer the distance between two nodes, more the time has passed, elapsed between the two nodes and vice versa. So, this is not that kind of a tree, this is a much simpler tree where we are just showing the relationship and nothing else. So, now given these terminologies, the question is how exactly does one get these kind of trees, particularly from sequence data. Okay. Once you understand how it happens from sequence data, you will realize that how it comes from morphological data is also very similar, but let me particularly give you an example using a sequence data. So, let us assume that we have three species, okay, we will just call them 2, 3 and 4, these three, and let us say we are interested in understanding the relationship, evolutionary relationship between the three of them. So, basically we want to know who came from whom, and roughly speaking who diverged earlier and who diverged later. Now, these three groups in which we are interested, these are what are known as the in group. Okay. Now, in order to do this kind of reconstruction of the phylogeny, we require one group which we definitely know is not a part of the in group. Okay. We are not interested in it, and we definitely know that this is something that diverged much earlier than the in group. and in this particular case that happens to be this species 1, and this is the one that we are going to call it as an outgroup. Okay. These are technical terms. So, the whole idea is that we start with the assumption that the outgroups sequence is the ancestral form, and essentially the question we are asking is that how does one go from the outgroups sequence to the various in-group sequences. In other words, what kind of mutations need to happen, what kind of changes need to happen to go from 1 to the existing patterns of 2, 3 and 4. How does one do that? So, let us see. So, remember we said that the outgroup sequence is the most ancient one, right. So, we take that right over here, and therefore, we assume that the outgroup splits right at the beginning and it has not changed ever after. So, this is my outgroup 1. Then we assume that this outgroup split or rather this common ancestor of the outgroup and our in groups, they split at some point, this is over here. Okay. And then from here this split into 2 sections. Okay. One lineage two lineages actually, one lineage had this mutation, this one, which converted the A at the 9th position to a T. Okay. Remember that there is only, this is the only difference between 1 and 2, this A at the 9th position has become T. Okay. So, that is this mutation, and let us assume that the other lineage that at some point acquired another mutation, and after that mutation this common ancestor of split into 2 groups, and one led to 3, the other led to 4. Why are we assuming this? Because remember 3 and 4 they actually have an more or less identical sequence, and the main thing is that both of them they have this A over here which is different from this T, and they have this A over here, okay, which is the same as this one. So, basically they are differing from this at exactly one locus. Okay. So, we end up So, if we end up thinking of it like this, then we can see that just 2 changes are enough for me to get all the sequence information that we have, right. So, we just need to assume that one change has happened in this lineage and another change has happened in this lineage at this point before this common ancestor, and that is it, we will get this back. Now, obviously, this is not the only way to get to this result, there are other ways too, but in these other forms you will see that you actually need to posit much greater number of changes in order to reach the same situation. So, for example, suppose let us look at tree number 2. So, in tree number 2 we can assume that this the outgroup split, and after that there is a common ancestor for 2, 3 and 4, and for this common ancestor for 2, 3 and 4 one lineage had this mutation, this 3rd position T becoming A, and in the other lineage again there was one split over here, one common ancestor, and this lineage over here this has this mutation, this 9th position mutation, and the other one has this mutation, other one has again the same 3rd position A goes to T mutation, okay, sorry, T goes to A mutation. If you do that, you will essentially recover the same tree, but when you are doing this, remember you can see that you have to posit at least 3 mutations to get to this. The same situation over here, here just 3 and 4 have interchanged places. So, again you need to posit that you require at least 3 mutations. So, what we are seeing is that there is one tree in which I can do it with just 2 mutations, but there are 2 trees in which I can do it with 3 mutations. Of course, there are other trees possible which will lead to the same results with many more mutations, but there is no other tree which will lead to this same result with less than 2 mutations. So, what we say is that this first tree which leads to a relationship with the least number of mutations, that is the most parsimonious tree. That is the tree which is the which requires us to make the minimum number of assumptions about mutations, and that is why we assume that this first tree is the correct relationship between these 3 species 2, 3 and 4. Now, this is just one way of making a tree. Okay. I am not saying that this is the way of making a tree. There are many other ways, and given various kinds of biological realities, sometimes the other ways of making the trees are more powerful. However, this way of making a tree is actually the simplest for us to understand conceptually. And incidentally, this is more or less what is done even in the context of characters. So, when you are looking at morphological trees, mostly people use this parsimony method to figure out what is the evolutionary relationship. So, for example, if you take all the properties of all the vertebrates and you try to classify them in terms of their evolutionary relationship, you will see that at some point the vertebrae arose, obviously that is how you are having vertebrates, and then those are the sharks, and then at some point the skeleton becomes bony, and from that, after that you get the ray finned fishes. Then at some point we develop 4 limbs, that is where you have tetrapods. So, these are the last tetrapod ancestor, and then these tetrapod ancestors they diverge to become the amphibians, but one group of tetrapods they ended up having what are known as amniotic eggs. So, if you look at the eggs of fishes and amphibians, they have to be laid in water, because they are extremely sensitive to desiccation and they cannot be laid in normal air, they will simply end up drying up. So, at some point the tetrapods they ended up coming with basically watery eggs. So, if you remember the egg of a chicken, you will see that there is a outer hard shell and there is a membrane known as the amniotic membrane, which essentially makes sure that the water inside is not dried up, not desiccated out, and that is why the egg, the developing embryo is actually able to develop in essentially a watery environment. So, that is what is known as the amniotic egg. So, then you have this ancestor with the amniotic egg, common ancestor, and one group ends up developing hair on their body. These group then split, one side one lineage becomes the primates, another lineage goes and becomes rodents and rabbits. On the other hand, the common ancestor with amniotic eggs, at some point they develop what are known as 2 post orbital fenestrae. So, basically this is the orbit of our eye, and behind this orbit there are holes. Okay, these are known as fenestra, and this group of organisms which leads to the dinosaurs and birds on one hand and crocodiles on another, these are the organisms which actually have 2 such holes, which allows among other things for jaw muscles to attach. So, this is the evolutionary relationship between these various organisms, and this essentially can be made based on precisely the kind of logic, parsimonious logic that we applied for the sequence case. So, anyway, this was all about how does one make trees, particularly using sequences. But remember, our primary question is that if we have trees that have been made using one method, let us say using morphological data, and trees that have been made using other methods, then how well they are corresponding with each other. We said that they are corresponding fantastic, and then we said that even trees which are made with different genes or different proteins, even they correspond very well to each other. Now, that is the one for which I want to give you an example. So, in 1982, Penny et al. They took 5 different proteins from 11 different species of mammals and essentially sequenced them. Now, they built trees based on phylogenetic trees based on the same logic that I talked about, and given the number of species and given the number of proteins, the total number of possible trees is 3,44,59,425, which basically means more than 34 million, right. Now, if these proteins are not if these mammals have not descended with modification, then we do not really expect them to be related to each other, and then we do not really expect the trees to be very similar to each other, particularly given that more than 34 million of them are possible. However, if they are related by DWM, then the across species relationships showed by these different proteins should actually be extremely similar, which is exactly what we get. When we look at the most parsimonious trees for each one of the 5 proteins, we find that they are very remarkably similar to each other, and the major relationships between which group which mammals are clustering with each other and which are clustering away from each other, that major relationship is actually remarkably conserved. So, as I said, if the 11 species had originated independent of each other, then the probability of the trees constructed out of 5 different proteins being similar would have been actually infinitesimally small. The fact that they were similar is showing unequivocally that they have come about due to descent with modification. And again, remember, this is just for 11 mammals. You do it for many other organisms, you keep on getting back this observation that when you do it with multiple traits or when you do it with multiple protein sequences or gene sequences, you are getting back very similar trees. And this fact that it is generally true across all living organisms is what makes descent with modification such a strong evidence, or what makes phylogenetic trees such a strong evidence for descent with modification. To quote Charles Darwin himself, this is a long quote. So, this is one of those old style sentences where one sentence is half a paragraph kind of thing. So, I have kind of broken it into multiple pieces so that we can parse the sentence better. So, Darwin says that all the difficulties in classification are explained. Okay, so, wherever you have those dot dots, those are the places where I have just edited out certain words simply because they are this is making the flow better. So, all the difficulties in classification are explained on the view that the natural system is founded on descent with modification. Okay. So, difficulties in classification are explained if you assume DWM is correct, that the characters which naturalists consider as showing true affinity between any 2 or more species are those which have been inherited from a common parent. Okay. So, all the most important characters, they have all come from common parents, and that community of descent. Okay. So, basically different groups are descending with modification in different lineages is the hidden bond which naturalists have been unconsciously seeking. So, this is a statement which shows the importance of descent with modification in understanding how different lineages have originated. However, taxonomy or phylogeny is not the only evidence in favor of descent with modification. There are actually many more, and that is what we are going to look at in our next discussion. Thank you.